Hello and welcome to our Physical Sciences Just-in-Time Revision Session, proudly brought to you by Saibono Discovery Center on behalf of Gauteng Department of Education. My name is Themba Ncube. Today we are focusing our attention on the physics paper, which is basically your paper one. Now, grade 12 is just on the eve of our Physical Sciences preliminary examination for 2022. Now, we may not necessarily, cover all the things because of the time constraints. I just need to caution you, but we shall most definitely prioritize those areas where you can most definitely, get the full marks. Now, without any waste of time, let's briefly talk about the structure of the paper itself. Now, it's 150 marks, which is 3 hours. Two sections, section A and section B, right? Now, what is important is that, you have got that 10 minutes reading time, before 9 o'clock, between 8:50 and 0900 hours. So what you're basically going to do while you are reading through the question paper, kindly identify those questions that you most definitely think that perhaps you could score, most marks. The thinking behind that is basically to say that if you start with questions where you can get, a lot of marks, you can actually boost or enhance your confidence going into other questions that might be a little bit of a challenge on the day. So it's very important in terms of approach. But if you look at the first section, which is section A, which is the multiple choice questions. Now, if you talk of the multiple choice questions, it's 20 marks. Then it means you can't say, for example, leave 10 minutes to do the 10 questions. You need absolutely, a longer period of time to respond to the multiple choice question. Now, just as a point of takeoff, I just want to talk to the technique which one may use, to answer multiple choice questions. So under no circumstances are you going to leave a multiple choice question unanswered, right? But also there is a technique to it in terms of enhancing your chances of, scoring the most or the maximum marks. Now, let's look at an example here of a multiple choice question. It talks of a box of mass M, right? So immediately it says M. There's no way you're going to use a calculator. So most of these physics multiple choice questions, they actually test your conceptual understanding or how well do you know or how you remember your stuff. So this box is of mass M. It is pulled over a rough surface. Okay. Now, the moment I see those key terms in the problem statement, rough surface, what exactly does that mean? You begin to ask yourself those very important questions. So if it's a rough surface, it tells us that, for argument's sake, there is a kinetic frictional force. Why kinetic? Because it is being pulled. So the object is already in motion. So there is a kinetic frictional force acting on an object. It is pulled by a horizontal force F, right? Which one of the forces below is the contact force exerted by the surface on the box? I normally say that all forces are applied forces. Okay, the word applied can be used interchangeably with the word exerted. So a force is always exerted by something on an object, or come to think of it, a force is always, acting on an object exerted by something else. Now, the problem statement says to us, this force is a contact force, right? So whatever exerts a force on this box, it is in contact with the box. That's what it means when it says it's a contact force. Now, there are 4 options that have been given. 2 of these options are totally out. We call them the distractors. So if you eliminate the 2 distractors, you're left with 2. Say for argument's sake, you get stuck. There is no way that you leave it blank. You choose from these 2. By so doing, I think you better your chances of getting the question correct or answering the question correctly rather, or than choosing randomly from 4. If you choose randomly from 2, you've got a 50% chance of getting right. But if you choose at random from 4, your chance is 25%, which is half. So by eliminating, you actually better your chances of, getting that question or that correct answer. Now, by so doing, I think you also try and even boost your marks. So today we'll talk a lot about the technique. Now, if you look at this, it says a normal force. Okay, let's interrogate that. What is a normal force? Let's try and describe this force in terms of exerted by something on an object. Now, a normal force is an applied force like any other force, okay? But exactly what exerts the normal force on an object? It is exerted by the surface on the object. So the object must be in contact with the surface such that that surface can exert a force perpendicular to itself on the object. So yes, we are happy with that. A normal force is a contact force exerted by the surface. We are happy with that. What about the kinetic frictional force? What exerts the kinetic frictional force on an object? Okay, we think, okay, it's the surface. But how is it different from the normal force? Yes, it is a contact force. It's exerted by the surface on the object. But now this object, this object must be in motion, and this force acts in the opposite direction of motion. So yes, it is a contact force. Okay, let's go on. Then C says weight of the box. Alternatively, weight of the box is actually the force of gravity or the force due to gravity, right? It's not gravity, it's the force due to gravity. Now, what exerts weight on an object? It is the center of the earth on the object towards the center of the earth. So it's by the center of the earth on the object towards the center of the earth, which exactly explains why the gravitational force always acts downwards, because the center of the earth is downwards. So even if you think of it in terms of the universal gravitation, it says to us that it's the force exerted by the center of the earth on the object, because these forces act because this object tends to pull each other towards their centers. So this one would be totally out because it's not the surface. It's essentially by the center of the earth. So we'll eliminate C, right? And then D says resultant of normal force and kinetic frictional force. Suppose this was our box, okay? There is our box. There is the surface, okay? Where is the normal force? There is the normal force. There is the kinetic frictional force, F, K, right? Now, the resultant of these two is actually the contact force exerted by the surface, because now these two forces are actually exerted by the surface. So if we eliminate that, okay, we're left with 3. Now, if A and B are both correct, then we're looking for an option that says both of them. It is for that reason that we'll come up with option D. Right. So this is a technique. It's not so much about the concept itself. My focus now was for us to go through the technique that one might use to, respond to multiple choice questions. But do not leave the multiple choice questions unattempted. Okay, that's the worst that one can do. So try and employ the technique of eliminating. With the hope that while you eliminate, think of the reason why those options are distractors. Think of them in terms of them. Why are they wrong in the first place? Right. Okay. So that was the first part there. Okay. Now, here is another very, very important part in terms of the quick wins. Now, let me define quick wins. Quick wins are your easy marks. That's a fancy way of saying, where can we get these easy marks? Everyone must be able to pick up those marks at the end of the day. Okay, it's granted, it's a given. Right. Now, definitions. There's only one source where we obtain the definitions. By now, I think we've gone through this multiple times before with your teachers, even in daily activities. Definitions, it's from the examination guidelines, because there's a lot of textbooks that we use. But what is acceptable in terms of definition in science are those that are prescribed in the examination guidelines. So in the event that we've not interacted with that document, I want to draw your attention to it. For every topic, any definition must be in the examination guideline. Okay, so that's the first part. Now, what do we mean by definitions being all or nothing? Okay, right. It's either you know your definitions or you don't. That's the thing. And then in the event that you don't, what is it that you do between now and November, when you write the final exam? Go back again, look at those definitions. If it's all or nothing, it means it's either you get 2 marks or nothing. Okay. If you are given a statement, okay, which of the following statements correctly describes the normal force? Okay, you need to understand that it is the force exerted by the surface on the object perpendicular to the surface. So there are keywords there that must be captured in the definition for you to earn those 2 marks. So pay careful attention to that. And not only do you include the keywords, these keywords must also be used in the correct context. What exactly do we mean? Let's break it down. When we say that the keywords need to be used in the correct context, it simply says to us that, look, when you read the definition, it must convey the correct scientific meaning. That's what it means. So pay attention to the keywords, use the keywords in the correct context. That's very important. Why are definitions essentially our quick wins, or a very, a bigger portion of our easy marks? Because it's either you know or you don't. That's the lowest level. You need to remember the definition, right? So, and all the long questions in section B, the 130 marks. Remember, section A is 20, and then section B, long questions is 130. You add the 2, you get the 150, which gives us the 3 hours in terms of the duration, right? So now, every long question in section B has a definition or 2. So you can by no means skip a question and not attempt at all. So it means that these easy marks are there for us to pick them up. It will also boost the performance, right? Okay, now let's go into the crux of some of the very, very important concepts. Like I said, with the physics multiple choice, you'd have noticed this by now, even from grade 10, that these multiple choice questions, many a time, they don't actually test your calculation skills and whatnot. It tests how well you understand the science. How well do you know your stuff, right? Let me make a practical example. Newton's laws, there's 4 of them, okay? But then we talk of the 3 Newton's laws that we covered in grade 11, okay? But everything else started in grade 10 when we looked at vectors and motion in 1 dimension. So it all, comes together in this 3-year course that we call metric. So your metric actually started, in grade 10, 2 years ago. Okay, so this is the 3rd year, right? Now, if you look at the first part, which says the Newton's first law there, okay, the key thing about the Newton's first law is that 2 things may happen to an object. It's either the object is at rest, okay, or it maintains its position. That's what we mean by rest, not moving, or the object moves at a constant velocity. And the key conjunction there is or. So, or it's either this or that. It cannot be both of them at the same time. So, according to Newton's first law, this object is at rest or it moves at a constant velocity or constant speed. So in the problem statement, pay attention to those keywords because they carry a lot of scientific meaning. Now, what causes the object to remain at rest or to move at a constant velocity? It's a zero net force. So according to Newton's first law, as long as the net force acting on an object is equals to 0 newtons, what that simply says to us is that the object maintains its position, it is stationary or it is at rest, or it moves at a constant velocity due to this zero net force acting on the object. You can also think of it in terms of the object is not accelerating because there's a zero net force. Right. Now, if there's a zero net force, the object does not accelerate. And what kind of motion is there for us to say the object is not accelerating? It's either the object is stationary or it's moving at constant velocity. So most of the problems that will follow up from the problem statement are based on your understanding of the problem statement. Now, once the net force is non-zero, what happens to the object? The object accelerates. So if the net force is 0, the object does not accelerate, stays at rest, or moves at constant velocity. Once there is a non-zero net force, it takes us to Newton's second law. There it is. So once there's a non-zero net force, the object accelerates. While the object accelerates, it means its velocity is changing. It's no longer constant velocity or constant speed as we captured it in the first law. So there's a very important distinction between the first law and the second law. First law, zero net force. Second law, non-zero net force. Then we can go on to talk about the relationship that exists between acceleration and net force. Okay, right? Acceleration and mass of the object. All right. So this is how we need to conceptualize these Newton's laws. Then you also realize that first law talks about a single object. Second law talks about the single object. But when you come to Newton's third law, it talks about two bodies, object A and object B. Force exerted by object A on object B is equal in magnitude to the force exerted by object B on object A. So these forces are equal in magnitude but opposite in direction, right? So that's very, very important. Hence, force by A on B, in this case, is captured as positive, okay? And the positive in this context of vectors simply means direction, okay? So if we have, say, for argument's sake, two objects collide like this, right? Object A exerts a force on object B. Simultaneously or at the same time, B exerts a force on A. These forces exerted on each other, they are of equal magnitude, yet they act in opposite directions. That's the long and short of it. Okay, so as we prepare for our prelim exam, those are the very, very important things that one needs to kind of capture. Right, so in as far as the application of Newton's laws, this would probably be your second question in section B. That would be question 2 in section B. It requires a lot of understanding, but beyond that, you need to read carefully the scenario before attempting to answer the question. What does it mean when we say you need to read carefully? Highlight or underline the keywords. Words such as rest, words such as stationary, which is they can be used interchangeably to refer to one and the same thing, an object maintaining its position or not moving. In both cases, the object experiences a force of 0 newtons. Then while it accelerates, it means there is a non-zero net force. So F net is not equal to 0. So F net is not equal to 0. That's what we mean when we say a non-zero net force. Okay, those are the key things. Right. Okay. Furthermore, grade 12, when it comes to this application, you can't talk about motion of an object without making reference to a force. Okay, the rest, stationary, acceleration is a result of forces. Okay, so understanding the forces is very, very important, and there will definitely be a question on the free body diagram under Newton's laws, under linear momentum and impulse. It could be projectile motion, work, energy, and power. So even in electrostatics, you have to draw a free body diagram, right? So now, if you underline the keywords such as rough and smooth, this is an indication of whether there's a kinetic frictional force or not. So before you even attempt to draw the free body diagram, carefully go back to the problem statement, study the sketch or the figure that might be provided or the illustration, and try to make sense of it. Okay, and then also on the free body diagram, it's also very important that you pay attention to the mark allocation. I mean, we've been saying this from grade 10 that if a free body diagram or a force diagram is 3 marks, it simply means that there are 3 forces. If it's 4 marks, there are 4 forces, and so on. So pay careful attention to the mark allocation, right? Now, and then there'll be a question that will say, for argument's sake, calculate the kinetic frictional force. Okay, first things first, Fk is equals to mu K multiplied by the normal force. This formula is given in the formula sheet. It's for you to copy as it is without making any attempt to change the subject. Okay, so the expectation is that you copy the formula as it is, and then in the event that there are forces that act at an angle, while we draw the free body diagram or the force diagram, we are not allowed to resolve. Just identify the forces as they are. You are not expected to resolve those forces while the question focuses on the free body diagram. Okay, so that's very important. Okay, and also speaking of forces, a force is a vector quantity. Pay attention to the direction. So if this is a force that pushes or that pulls an object to the right, if you write it and represent it like this, it's just a scalar. Why? Because it doesn't show or indicate the direction. So make sure that you also include the direction. So for each mark, it's for the correct force that is labeled. Let's say this is an applied force and the direction is also indicated. All right. And then for other calculations that we would want to refer as the multi-step problems. So if it's a multi-step problem, it means you actually have to do multiple calculations. It's not a routine calculation where you just indicate the formula, the substitution, and the answer. Okay, that's 3 marks for each, 1 mark for each, so it will give you 3. But once a calculation is 4, 5, 6, 7 marks, right, it means it's a multi-step type of a problem. You have to find something, use that something in another equation to find something until you get to the correct answer. Hence, we call it the multi-step type of a problem. So pay attention also to the mark allocation, because it tells you that it's a simple case of formula substitution and answer. Formula, data sheet. Substitution, make sure the necessary conversions to SI units have been carried out, right? So if the mass of the object is given in grams, you have to change it to kilograms, distance to meters, and so on, right? So that's out of the way. Now, we cannot do anything without the data sheet. By now, you are familiar with the data sheet, but do not be complacent. Go back to the formula sheet, identify the correct formula. This is a practical example of the formula that I used in the previous slide. You copy it as it is. Just for copying it, you get a mark, provided you also make an effort to substitute something somewhere. So the 3 marks is actually for everyone to get, right? Okay, so that's our data sheet, which will be provided. So there's absolutely no reason why you need to memorize all these equations, because at the end of the day, they will be given after all, right? Okay, let's make a practical example in terms of the, the strategy that we've just discussed up to thus far. We've got an 8 kg block that is pulled by a constant force F up a rough inclined plane. I'm going to underline the word rough. Okay, this is exactly what you do, because there's quite a lot of implications in as far as that very, very important term, right? So rough suggests that there's a kinetic frictional force acting on the 8 kg block. Okay, now force F is parallel to the inclined plane as shown in the diagram. Now this, I've indicated this state, that is an action verb, right? So pay attention to those keywords. If the question says state, it's the same as define. Okay, it's either you remember or you don't. Okay, so if you want to state the Newton's first law, it says in words. So we don't accept equation. So you're not going to write F net is equals to 0 newtons. That's why it says in words. Okay, now you go on to state the Newton's first law. If you remember it very well, you'll get the 2 marks. It would say then an object, it talks about a single object, will remain at rest or move at a constant velocity unless or otherwise acted upon by a non-zero net force. So that's 2 marks or nothing, right? What is of interest to me now is the question on the free body diagram. Okay, every calculation that will follow up will be based on the free body diagram. So pay attention to the problem statement and also the mark allocation. So for this free body diagram, it's 4 marks. What does that tell us? Okay, we've discussed this. It says to us that we need to indicate 4 forces. Okay, so we've got, this is the object, right? We are allowed to put even the incline, okay, to include the incline. There it is. Okay, there is this force F acting on the object, right, up the incline, right? And then we've got the weight or the force of gravity which is actually exerted by the center of the earth on the object towards the center of the earth, which explains why Fg always works acts downwards vertically. And then we've got the force, another contact force exerted by the surface on the object, perpendicular to the surface. Perpendicular, we mean that force acts at an angle of 90 degrees to the inclined plane. And we need to get this right. The normal force does not act upward, so that we are careful with that. It acts perpendicular to the surface. So if the surface is horizontal, the normal force will be vertical. But if it's an inclined, it will act still perpendicular. In both cases, it's correct, right? So that's our normal force, right? So now we've got 3, and then we have the force that opposes motion. Motion of this object is up the incline. So this is the kinetic frictional force. So for each one of those forces, you actually get a mark, right? Okay, and then another part which talks about the Newton's laws, very, very often neglected, and in my opinion, it's actually one of the easy marks that each one of us can grab here and there, right? We've got 2 objects, A and B, of masses m1 and m2. They're at a distance d, right? So if I can maybe sketch this, we've got this object, that's m1, okay, that's m2, right? The distance between their centers is d, right? There is the scenario, okay? The force that A exerts on B is F, okay? Both masses are doubled, right? What is the new force that B exerts on A in terms of F? We are very familiar with these questions, but it doesn't take one to guess. It's very important that, okay, first of all, we locate as to which concept is involved here, what science is around this problem statement. It's obviously the law of universal gravitation. Number 1, you must be able to state it. Number 2, you must be able to go to the data sheet, extract the formula as it is, and copy it if it's a calculation. So in other words, what this question says is that if it's based on the universal gravitation law, is going to be F is equals to G m1 m2 over d squared. This is F, right? Now, what will happen if we double both masses? So this becomes, instead of m, it becomes what? 2m1. Okay? This becomes what? Okay, and the distance between their centers is halved. Okay, it's fine. We double both masses. This is 2m2. Now, the distance, instead of d, it becomes d over 2, right? This is what it means, okay? Then, we want to express the new force in terms of what? In terms of F, right? So what has happened here? We've got G, the universal constant, 2m1, 2m2, right? Divided by d over 2 squared. So we are squaring half the distance. We are not halving the square of the distance. So there's a bit of language there. So the distance has been halved from d to d over 2. So what we are squaring is half the distance, right? Then this takes us to, obviously, it will give us a 4g, right? m1, m2 divided by d squared over 4, right? So if it's divided by d squared over 4, it's the same as saying 4 multiplying by 4 over d squared, right? So this will take us to 4 times 4g, right? m1, m2 over d squared. But this is exactly what? Our f. So this takes us to 4 by 4f, which is 16 times f. But maybe before that, what is important is that we need to check before we eliminate the answers to say, while we double both masses and half the distance, will the force increase, decrease, or remain the same? Okay, so doubling both masses will increase the force. Having the distance will increase the force. Now, then we zoom in. If we double both masses, the new force will be 4 times the original one. While we have the distance simultaneously, or at the same time, the new force will also be 4 times the original. So it's 4 times and 4 times, which means it's 16 times as big, right? So then that takes us to option D. So that's also, you can also use the very same approach when it comes to your electrostatics in terms of Coulomb's law. We use the very same approach. We ask ourselves, what's the relationship between the product of the charges and the electrostatic force? What's the relationship between the electrostatic force and the square of the distance between the charges? So this is an approach that we use. And then question 3 would most likely be on vertical projectile motion, which also in many ways talks about forces, maybe a force, if not a multiple forces, right? So the key words or the key terms or concepts that you most definitely can predict that will be asked. You must always anticipate that. If they don't ask you, or if you're not asked to define free fall, you might be asked to define a projectile, right? I'm saying a projectile, right? So free fall is the type of motion, right? Free fall is the type of motion, right? Free fall is the type of motion. And then an objectile, a projectile is an object rather, okay? Right, so you need to distinguish this. So what type of motion is free fall? It is motion of an object under the influence of gravitational force only. And I'm saying gravitational force, not gravity. Gravity is a phenomenon. Gravitational force is a force that exists as a result of this phenomenon of universal gravitation. I think it all comes together in that way. So while a projectile is an object that is given an initial velocity, okay, and after that it moves after under the influence of gravity, right? So in other words, a projectile undergoes free fall, but not all projectiles are not all free falling bodies are projectile, because if we drop an object like this and ignore effects of air resistance, that object moves under the influence of gravitational force only, but it's not a projectile. Why? Because it wasn't given that initial velocity. So go back to your examination guidelines and try to make sense of that. Now, 2 things are very, very important in free-falling bodies, right? Or in projectile motion. Once there is only one force acting on an object, that force becomes the net force. And in which direction is that force? It's downwards, because the only force that acts on the object is the force of gravity. Now, if a net force acts downwards, the acceleration will also be downwards, according to Newton's second law. What does the Newton's second law say? If a net force acts on an object, the object accelerates in the direction of the net force. So what that simply says to us is that while the net force acts downwards, that's exactly the direction of acceleration. So 2 things are very, very important in free fall, okay? In this type of motion, only the force of gravity acts on the object, and as a consequence or as a result of that, the object will accelerate downwards, and it will undergo a constant or a uniform acceleration of 9.8 meters per second squared downwards. It's supposed to be squared there, right? Then downwards is the direction. So that's magnitude, that's direction, right? So what does this mean? Because acceleration is change in velocity per unit time, then it means the velocity of the object changes by 9.8 meters per second for every second, right? So it means the object either moves faster and faster downwards. For every second, the velocity will change by 9.8. If an object is launched vertically upwards, this velocity will change by the same amount. However, while it moves upwards, it moves slower and slower, or the velocity decreases by 9.8 meters per second for every second. Okay, right. And then the key word for us to classify a certain type of motion as free fall, we need to pay attention to the words that, like, air friction is ignored, or ignore effects of air resistance, or ignore air friction, right? So once we ignore air friction, it means there's only one force acting on the object. So the free body diagram of a free falling object has got 1 mark. Why? Because there's one force. Remember, we said we need to pay attention to the mark allocation. So if an examiner says to you, draw a free body diagram of a free falling object or a free falling body, it's going to be 1 mark. It says you only draw a single force. Okay, all right. So the only force acting is force of gravity, right? That force acts vertically downwards, which is the direction of acceleration according to Newton's second law. Okay, so this object experiences a constant or a uniform acceleration. And another very, very important part of kinematics or vertical projectile motion is that there are equations of motion. Routine calculations, 3 marks. Formula, substitution, answer. But the answer must include the correct SI unit. Right. Okay, let's look at some of the tips for the calculations based on VPM. Okay, so you need to read the scenario carefully before attempting to answer. That I'll always remind you. Very, very important. And then draw a trajectory of the object if it is not given. Let me explain briefly what a trajectory is. It's that sketch which shows the path followed by the object. So if we launch an object from the top of a roof, so we'll draw a line showing the object moving upwards, coming down, back to the roof. In some cases, it goes further down to hit the ground. So that sketch is what we call a trajectory. Why is it so important? Because here we talk of vector quantities. So we consider motion between any 2 points, right? Position, displacement, velocity, and acceleration, all of them are vectors. They've got both magnitude and direction. And once we ignore those, then that throws us under the bus, which is definitely what we don't want, right? So you need to choose direction carefully. I've alluded to this earlier to say the plus says maybe to the left or to the right, meaning negative will be in the opposite direction in a straight line, all right? Okay, now you always consider motion between 2 points. I've also spoken about the formula sheet, right? Let's look at a practical example, right? A small stone is projected vertically upwards. Now, if I may pose a question there, is this stone a projectile? Most definitely, because it wasn't dropped or released. It was given an initial velocity for it to move vertically upwards. So this stone is a projectile, okay? That is out of the way. From the ground, we're given the speed of the ball, okay, of the stone. It passes the roof that is 8 meters of an 8 meter tall building on its way up, and it reaches the maximum position or height A. So this is the maximum height, right? On its way down, the stone passes the roof at point B as shown in the diagram. There is our famous statement, ignore effects of air friction. So if I were to draw the free body diagram for the entire motion of that stone, there is the dot that represents the stone, right? And then downwards, the force, then I label it. Right, so this is the free body diagram. So the acceleration of the stone while it moves from the ground to position A is downwards. Why is it downwards? Because the force, the only force acting on that object is downwards. It's the net force. Then the object accelerates in the direction of that net force. So we expect the velocity or the speed of the ball to decrease as it moves from the ground to position A. Why does it decrease? Because it's accelerating downwards. So in short, what we're saying is that if the stone moves vertically upwards, slowing down, its direction of acceleration is downwards, which is exactly the direction of FG. All right. Now, so this is a free falling object. Why? Because we've ignored air friction. Now, the question 3.1 says write down. It doesn't say calculate. You need to pay attention also to the language. So if it says write down the acceleration, okay, then wait a minute. Acceleration is essentially a vector. Now, this question is 2 marks, right? It's either you know or you don't, because you're not going to calculate. I can rephrase the question and say, what is the acceleration of the stone? If I say, what is your name? You answer directly. No explanation, nothing. You just respond directly. So the 2 marks, 1 mark is for magnitude, which is 9,8 meters per second squared. Then the other mark is for direction, which is downwards. Okay, so if it's downwards, it's in the direction of the net force according to Newton's second law, right? So that's out of the way. So it's magnitude and then direction. That's the 2 marks. Using equations of motion, calculate the time it takes the stone to reach point A. I may also rephrase the same question. Instead of saying directly calculate the time, I can say, how long does it take the stone to reach point A? Right. Now, according to the tips, we need to consider motion between any 2 points. And then it means the ground in this case is the initial position, and then position A is the final position. We want to determine how long, right? So we must capture the data correctly. What are we given here? We know the acceleration of this stone. Okay, if we choose upwards to be positive, say for argument's sake, it doesn't have to. If we choose upward to be positive, meaning downwards, which is the opposite direction, will be negative. So the acceleration of the object is in the opposite direction of its initial velocity, because while it was launched as a projectile, remember, it was launched upwards. So the initial velocity is upwards, the acceleration is downwards. So if we say upwards is positive, meaning the acceleration is negative 9,8 meters per second squared, while the initial velocity is positive 20 meters per second. Now, take note, the minus 9.8 suggests downwards, which is the direction of the net force, while initial velocity is positive, which suggests that it is upwards, right? So here we are looking for the time, okay, that it takes for it to reach the highest position. But what else do we know? We know that at the highest position, this object will come to rest because it's slowing down. The furthest that it can, or the fastest that it will move after it is slowed down completely, is that it eventually comes to rest, or it's momentarily stationary at position A, which is fine. Now, then you can go to your equations of motion, which is not of a particular interest to me. So this process of extracting the data and also trying to make sense of the direction of these vectors, it's also very important. Another thing that's also very important, grade 12, is that the time it's a scalar quantity. So I expect that you get a positive value for time if you did pay careful attention to the direction. Okay, so we have VF, VI, we've got acceleration. So this is 3 marks. Okay, so it's going to be VF is equals to VI plus A delta T. Right, now that's 1 mark for that. So VF is 0. Final, VF is 0, yes. Initial is 20, right? Plus minus 9,8 delta T, right? So delta T is the only unknown. So delta T, if you do your maths, there it will give you a value. If you go quickly to your calculator, you will get 20 divided by 9.8, right? Okay, so this gives us 2,04, positive 2,04 seconds. Right, that's the time it took the ball to move from the ground to the highest position. So there is the formula, is the substitution, is the correct answer. The correct answer must include the correct SI unit. Very, very important, right? Now, calculate the velocity of the stone at the instant it reaches point B. All right, now, this is a very, very important part of the calculation. Now, already you have the 5 marks, right? This is just a portion of the problem that I want to use for us to, get into a discussion of the technique. Now, if they want the velocity of the ball while it passes point B, one has to ask themselves a very important question. In which direction is the object moving, or the stone moving, when it passes point B? It's moving downwards. So that velocity must be negative according to our choice of direction, right? So, and also, if the ground is the initial position and B is the final position, then it says to us that the change of position from the ground to position B is in which direction? It's upwards. It's going to be positive, which is exactly that height. So this 8 meters is actually our change of position when we consider motion from the ground until position B, right? Say, now in this case, what we are simply saying is that, okay, we've got delta Y, the constant acceleration, which has not changed. We have the initial velocity, but we don't have the time. So we can use the equation VF squared is equals to VI squared plus 2A delta Y. Okay, now if you think of it, this is also 3 marks. It's a case of formula substitution and answer, right? We're looking for how fast it's moved at B, and B is our final position. So we do not have our VF. Okay, our initial squared is 20 squared minus for the 9.82 times 9.8 delta y, right? Right. So the delta y, we have the delta y, which is our 8 meters. So the change of position from the ground to B is in which direction? It's upwards. It's going to be positive 8. So this is actually a positive 8, right? So if you go to your calculator, you will get 20 squared, okay, minus 2 times 9.8, and then times positive 8, okay, right? 2 times 9.8 multiplied by positive 8, which is the displacement. Okay, it gives us that. So the 243,2 is VF squared. Now, if we are looking for the value of VF, we need to find the square root of that answer. This gives us what? Our VF is positive 15,59 meters per second. We take the positive one. Okay, why? Because it's moving downwards. Right. So also it's 3 marks, formula substitution and answer. Right. And then the total time it takes to move until it reaches the ground on its way down. Now, this is 4 marks. Without maybe getting into, the detail of what's supposed to happen there, it's 4 marks. It means we have to find something and then use that something in a follow-up step to get the final answer. In this case, is the total time. All right. But of particular interest to me is this one now. Okay. Sketch the velocity time graph of the motion of the stone from the instant it is projected until it reaches point B on its way down. It's 4 marks, right? Now, there is a change of direction because the stone initially moves up and then moves downwards. So first is the tightly V versus T, right? And then from there, we've got the vertical axis and then the horizontal axis. So that's time. You label the axis, okay? That's V in meters per second. Okay, that's 0. Now, if you look at the motion of that stone, okay, it starts with an initial velocity of positive 20, right? What happens to the stone as it moves upward? It slows down uniformly. Why uniformly? Because it undergoes a constant acceleration. Then it goes, that's our graph, okay? This is the time that it took to reach the maximum height. What was the time? Just to go back to that. The time that we calculated is the 2,04 seconds, right? So that's the 2,04 seconds, right? So this is 2,04, right? And then after that, it changed direction and moved downwards. But then when it reached point B, it was moving at 15, we need to just check to verify that value. It's 15,59 meters per second, right? And then this 15, it's actually going to be negative because it's moving downwards, okay? We need to rectify that as well, right? So it's going to be negative 15, this is negative 15, just to check that value, okay, 59, all right? 15,59, right? So this is the graph of motion, right? So if you actually look at this graph, it's a linear graph. That linear graph represents a constant gradient, and the constant gradient is A is equals to delta V over delta T. And then what does this represent? It represents exactly the acceleration of the object, right? Okay, that's as far as VPM. And then the other part also on mechanics, which has to do with linear momentum and impulse. You can't have one without the other. It also essentially deals with the forces. It might be probably your question 4, which says the following definitions are very, very key or important. You need to go back to your exam guideline, know what momentum is. Even the formula sheet will say small letter p is equals to m is equals to mv, right? Then Newton's second law in terms of linear momentum, the data sheet also captures that F net delta t is equals to delta p, which says this is change in momentum, which is equals to impulse. So that's our impulse there, right? While F net, okay, is equals to delta p over delta t. This is rate of change of momentum, which equals the net force. Now, you must know what an isolated system is in terms of a net force of 0. Okay, also remember what the principle of conservation of momentum, linear momentum, says in words. Okay, it's also based on the fact that it's a closed or an isolated system. And also try to remember the difference between an elastic and an inelastic collision in terms of the total kinetic energy initial versus total kinetic energy final after a collision or an explosion, right? So there are a lot of related concepts here, and there is no way that we're going to divorce it from the Newton's laws, because when objects collide or when there's an explosion, what actually happens is that there are forces that are exerted on the object by another. Okay, and once we say force by object A on object B, or force by object B on object A during that collision or that explosion, it takes us straight to the Newton's third law, all right? It takes us straight to the Newton's third law. So we know that change in momentum is delta P, which is actually equal to the net force and the product of the net force and time. So this is what we know already, right? Okay, and then what are some of the very important tips in as far as problems involving linear momentum and impulse? First of all, read the scenario carefully and underline the keywords, right? Also remember that most of the quantities except time, velocity, momentum, change in momentum, average force, are all vector quantities. So direction is very, very important. Okay, so whether it's a collision or it's an explosion, it's important to appreciate the sense of direction. Otherwise, there's no science, it's just numbers that are meaningless to us, right? And also pay attention to the mark allocation. We're saying the same and the same thing once again, right? Now, let me just use this example to talk about what you call vectors and why direction is of importance to us. Here, a ball is thrown towards the wall. Okay, if it's thrown towards the wall, it will collide with the wall. During that collision, the ball exerts a force on the wall and the wall exerts a force on the ball. So that's Newton's third law. The force exerted by the wall on the ball during the collision is away from the wall. That's why the ball eventually moves in that direction. I hope it makes sense. Now, if we're going to talk about the change in momentum of this object, as an example, change in momentum is a vector. Okay, it's let's say the object is of mass 2 kg, right? It's a heavy ball. Okay, 2 kg, right? Let's say it's gonna be mass change in velocity. That's what it is. Okay, now the mass is 2 kg, right? The change in velocity is final minus initial. But wait a minute, velocity is a vector quantity. If we say towards the wall is positive, it means away from the wall is negative, right? Okay, if that's the case, then we're saying it's going to be 2. Our final velocity is negative after collision. Our initial is positive. So our final velocity is negative 12 minus the initial velocity, which is positive 12. Okay, right? Then we have got 2 multiplied by negative 24, which is equals to negative 48 kg, right, meters per second. So the negative suggests that the change of momentum of the ball due to its collision with the wall is actually to our right or away from the wall. So that's negative suggests away from the wall. So we need to interpret that it's 48 kgs meters per second away, right, from wall, right, away from the wall. So this is a practical example of why vectors are very, very important. Okay, with that said, we shall take a short breather for about 5 minutes just to get some water and come back. Then we continue with our our revision session, which is proudly brought to us by Saibono Discovery Center in partnership with Gauteng Department of Education. See you after 5 minutes. Hello and welcome back to our revision session that's proudly brought to you by Psychobono Discovery Center in partnership with Gauteng Department of Education. My name is Temba. During the break, I tried to look at some of the questions that you guys have posted on the chat number. The one that came up once too often than others, obviously, is the one of when we draw free body diagrams. I think you get a sense by now that the free body diagram, in as far as the mechanics is concerned, is one of the very, very critical areas. Right. Now, there are acceptable symbols that we use to represent certain forces. F, small letter G, and then W, small letter W for weight, T, capital letter T for tension, FK. So go back to your exam guide. It will tell you what is acceptable in terms of notation. You don't necessarily have to describe the forces in terms of by-on. I think some of you were asking that question. All right. Now, because of time constraints, I just want us to quickly go to another concept that's, in my opinion, I think it's one of the areas where you can actually get a lot of marks. But now the problem is that some of you tend to skip this section, the one on electrostatics, right? Which is essentially grade 10 and 11 work. So I want to use the next few minutes just to remind you of what is important, okay? Now, the following concepts are very key. The principle of quantization of charge, the one that says Q is equals to NE, which is exactly this principle, right? Which talks about why an object is positively charged, meaning that a certain number of electrons was removed from it. So when you see Q is equals to Ne, Q is the charge, N is the number of electrons removed or added, and then E is the elementary charge, that negative 1,6 times 10 exponent negative 19 coulombs, right? So that's the quantization of charge. And then when it talks about the principle of conservation of charge, how do we tell that in a problem statement the question is about the conservation of charge? The scenario would say sphere A and sphere B are brought into contact and separated. And then it takes us to the one that says Q mu, okay, is equals to Q net, okay, divided by 2. That's the principle of conservation of charge, that when two spheres, two charged particles are brought into contact and separated, during that process, physical process of contact, they actually share charges, right? So remember this from grade 10. And then the Coulomb's law, which is F electrostatics, is equals to K Q1 multiplied by Q2 over R squared. And then we talk about the electric fields and electric field at a point. So the electric field is the region around the charged particle. Suppose we have got a positive point charge there, and then this is what is happening. We'll denote the field using the field lines like that. So if it's positive, it will be going out like that, meaning that if we place a unit positive charge there, that unit positive charge will experience a force away, because this charge is positive, it repels the other one. So that's an example of an electric field. And then electric field at a point, it's exactly this, right? And then we use this equation to calculate electric field at a point due to the charge that creates the field. Let me make a practical example of that, right? Say, for argument's sake, we are talking about the net electrostatic force that is exerted by charge J and K on charge J and L on K. So we have K there, right? K is a positive charge, right? Now, suppose this is K, right? Then L is positive. These are like charges, but in the sense that they are both positive. So L will push away K in that direction. So this is F due to charge L, all right, on K. And then charge J is negative. The force that it exerts on K is an attractive force towards itself. In other words, J pulls K towards itself. Then this is force due to J. Then, in other words, this is our F net, all right? Okay. This process is very, very important if we are to determine the net electrostatic force exerted by L and J on K. Then we can come up with our force diagram to say, okay, that's our F net. That's the direction of F net there, right? And then this is our F due to J, and then this is F due to L. They are perpendicular to each other. Then we can employ the theorem of Pythagoras. So these are 3-point charges in a 2-dimensional space. So the first point is to understand that like charges repel each other, while opposite or unlike charges attract each other. Now, it can be also a case of 3-point charges, charge R, T, and S. Okay, let's say this is positive 5 nanocoulombs, this is positive 4 nanocoulombs, and then this is negative 3 nanocoulombs, for argument's sake. So if we want the net electrostatic force, say on T due to R and S, so T will actually push R will actually push T away in that direction because they are both positive. Okay, so this is force due to what? To R on T. All right, and then S is negative. It will actually pull the same charge T towards itself. This is force due to S. So our net electrostatic force is to our right. Why? Because both of them, they exert a force to the right. So F net in this case is equals to FR plus FS. Okay, then they are in the same direction. So the direction of F net will also be to the right. Right. Okay, and then when it comes to electric fields, okay, the free body diagram, we're still talking forces. Even in the first segment, I think we tried to make sense of this. We've got those charges Q1, which is a magnitude of -6 times 10 exponent -9. That's like -6 nanocoulombs. This is like -8 nanocoulombs because it's negative exponent 9. So take note of also the conversion of quantities, or in terms of charge there, from whatever is given to the SI unit. So the distance between Q1 and Q2 is 3 meters. X is a point that is 2 meters from Q1. And at the same time, X is 1 meter from Q2. I think it makes sense because these two charges are 3 meters apart. So X is a point that is in the field of Q1. At the same time, X is a point that is in the field due to Q2. Right. So the question may say, calculate the magnitude of the net electric field at point X. So at point X, what do we do? At point X, we place a unit positive charge, right? That unit positive charge is placed at point X. Now, charge Q1 is negative. It will attract that. It will pull the unit positive charge to itself because this is negative, and then the unit positive charge is positive, as it suggests. So this is E due to Q1. What about E due to Q2? Q2 is also negative, okay? While the unit positive charge is positive, right? So the same positive unit charge would be pulled towards Q2, which is negative. So this is E due to what? Q2. So if we were to calculate E net at X due to Q1 and Q2, then we have got E net is equals to E due to what? Q2, okay, plus minus E due to Q1. Why am I saying minus? Because E due to Q2, if we assume east is positive, right, it means west will be what? Will be negative. Hence, E due to Q1 is negative. Why? Because it's westwards. Then it means then E net in this case is going to be what? E due to Q2 minus E due to Q1. Right. So that's very, very important. And while you substitute here, it's going to be K Q2 over R squared. And K Q1 over R squared. Please do not substitute the negative for the type of charge. Why? Because it will, it will mess up the direction. Because here there is a question of the negative charge and the negative direction in this case, which is west. So when you substitute the charge, never include, please do not include the sign of the charge. I hope it makes sense. Right. Okay, and then that's another practical example. It could be now P is a point. We've got Q1, Q2, right? So the free body diagram, once again, is very important before you do any calculations. So while you draw the free body diagram, you're actually doing the science, right? Which is the most important part. Once the science is right, the mathematics will follow after that, right? So we have got point P. At point P, we place a unit positive charge there, right? It will experience a force due to Q1, right? So Q1 is positive 3 microcoulombs. It will repel that unit positive charge. So this is E due to Q1, right? Due to Q1. And then Q2 is negative. That unit positive charge placed at point P will be drawn towards Q2 in that way. Then this becomes E due to what? Q2. Then the signs will follow thereafter. I hope it makes sense. Right. Okay. Another area that's in many ways learners tend to struggle, but not because the science is not there, but sometimes I think it has a lot to do with the technique in how you respond to these questions. Now, when you are given a circuit, there are those easy marks that are very, very important that one can actually pick up, right? So while you were going through the question paper in the 10 minutes reading time before 9 o'clock, you try and identify those questions where you'd actually get the most marks, okay? You'll start with those questions so that you also manage time better, because there is no rule that says you must start with multiple choice. Neither do you have to spend a lot of time and then 5 minutes before 12 o'clock you try to do the 20 marks in the multiple choice. That will obviously spare a lot of disaster. Right. Now, the key things here in this case, the key definitions, which are our quick wins, we're still focusing on the easy marks, right? The examination guideline will give you the correct definition of EMF. Okay, just to remind you, remember EMF is voltage. So V is equals to W over Q, as we know it in grade 10, right? So if we talk about EMF, we're talking about the maximum energy. W is energy, right? It's work. Work is energy. Energy is work. Why? Because we've been singing that energy is the capacity to do work. And if you check, we measure work in joules. We also measure work energy in joules. It means work is energy and energy is work. So that W stands for energy or work. It is one and the same thing. So it's the maximum energy per coulomb of charge that can be dissipated or that can be supplied by the source, which is the battery. Okay. Do not be tempted to use that version that talks about the EMF reading of whatever reading across the battery when there's no current. That speaks to the EMF reading, but in concept, in principle, EMF is a quantity. So you must define it in terms of the maximum energy per coulomb of charge. Then we talk about a terminal potential difference. This is what you would call your V external, right? Okay, and if you say V external plus V internal, that's where you get your EMF. That's where you have got that very important equation. E is equals to I, okay, R plus R, right? And then also think about internal resistance in terms of the experiment, because sometimes the examiner may ask you to talk about the variables, in an experiment, like in this case, the one of determining unknown resistance of a battery. You might have done that. I think how you remember that will also be very important. And then Ohm's law, which is V is equals to IR, in terms of the definition, go back to examination guideline. This is the same as the Ohm's law. Why? Because E is voltage, right? Then we've got current, R plus R, that's resistance. So that's V is equals to I, R, still the same thing, right? Okay, and then also some very important work from grade 10 in terms of series, parallel circuit, as well as power as we did it in grade 11 in terms of P is equals to VI, P is equals to V squared over R, and then P is equals to what? I squared R. There's also the ones on energy consumption and work, the tariffs. Now we're experiencing a lot of load shedding because of the consumption, levels of electricity. So the concept of power is very practical in that regard. Right. So that's our data sheet. Copy the formula as it is. Do not attempt to make any what you call manipulations or to change the subject as you do with the mathematics, right? So copy the formula as it is and try to familiarize yourself with the data sheet as much as you possibly can. But it's also important to copy it as it is given, right? Okay, here is a simple circuit. You see there are no questions because that's what I want us to try and, this is the attitude that we need to try to adopt. When the statement says, study the following circuit before and answer the questions, it means studying and understanding the circuit is the most important part of responding to that question correctly. So if you have a circuit of this fashion, you have those resistors. We can call this, let's say this R1, we can call this R2, we call this R3, and we can call this R4. So there are 4 resistors, okay? And then we've got this 12 volts. What is this 12 volts? This 12 volts is the EMF, right? E is equals to 12 volts, okay? Beyond defining what EMF is, an examiner may ask you to say, define an EMF of 12 volts, right? But we have already said that V is equals to W over Q, né? And then it means that if we've got a volt of potential difference, what it means is that we've got 1 volt, which is equals to 1 joule per coulomb, right? Now, if it's 12 volts, it means it's going to be 12 volts, which is equals to 12 joules per coulomb. Now, if we were to define an EMF of 12 volts, it means this battery can supply a maximum of 12 joules of energy for every coulomb of charge. That's what it means. If it's 24, it means it's 24 joules for every coulomb of charge. 24 joules of energy, 24 joules of work, okay? Because when energy is transformed from chemical potential energy to electrical, the battery in itself is doing work. So when energy is converted from one form to the other, it does work. That's why we say it's W there, right? And then also, it's important to realize that R3 and R4 are in series, okay? So in other words, we've got this 4 ohm, right? We've got this 4 ohm and this 16 ohm, okay? One would ask, where does the 16 ohm come from? Okay, the 16 ohm comes from the 8 and 8, which are connected in series, right? So this is how we would represent the very same circuit. Okay, now all the current goes through that ammeter, right? So it's the 4 and the 16 in parallel, and then the 2 ohm is in series, right? So the internal resistance, small r, is actually in series with the external resistance. That's why we have R plus R, because these two are in series. Remember, R series is R1 plus R2 plus Rn for n resistors that are connected in series, right? So this is how you would try and attempt the questions on the circuit, right? So if you look at it again, the V for R3 and the V for R4, okay? Then let me call this V4, right? Right. If you add this V, let me call it V3, okay? If you say V3 plus V4, you must be able to get V2, okay? There's a very important scientific fact there. Now, the 4 ohms is parallel to the 16. And what is it that we know about a parallel circuit from grade 10? We know that potential difference remains constant, right? So, however, R3 and R4 are in series. It means this is equals to V2, right? It means then voltage of across this 4 ohm resistor is the sum of V3 and V4 because they're in series. So if you add V3 and V4, it must give you V2, right? And then the voltage across the 2 ohm, if you add it with the V parallel, it must give you the V external, right? So there are a lot of things that you can do with a circuit without necessarily, looking at the questions. While you study the circuit, that's what it means, or it entails to say study the circuit. Already you would have answered some of the questions that will follow up. Unlike looking at questions and then trying to cut and join and put figures, there wherever you see voltage, you just plug it in. That's where you lose marks. So while you study the circuit, ask yourself the important questions. Is this a series circuit? Is it a parallel circuit, or is it a combination of a series parallel, or is it a parallel series? So those are some of the things that one needs to remember, right? Okay, the other thing that's also important, just to remember, to indicate that internal resistance in any problem, there are two things that might happen when it comes to internal resistance. It's either it is given or it is unknown. So it could be one of the two. And in either way, it's not a train smash. One is able to work around because the information can be obtained while we study the circuit. Right. And then another very important easy mark type of a question is the one that has to do with electrical machines, electrodynamics. And also this one, unfortunately, it starts in grade 10 where we look at magnets. Grade 11, we look at Faraday's laws of electromagnetic induction. So go back to the exam guide, remind yourselves of those key definitions, look at the keywords, try to rewrite them just to remember them, because that's how we actually get marks, right? Having said that, so that's the Faraday's law, which talks about the relationship between induced EMF and the rate of change of magnetic flux. For now, we don't calculate the magnitude. We only are required to know the factors that would actually affect the magnitude of induced EMF. Okay, but this has to do with what? Generators. Okay, so hence there's this very important question which says, on what principle is the operation of a generator based? It's actually based on Faraday's law of electromagnetic induction. Okay, right. And then the motor effect, right? This has to do with what? Motors, because it's the motor effect. Okay, but also those two are very important in terms of, trying to distinguish them in terms of, the components of the each of those machines. And in all cases, you're always given a simplified machine. Okay. Also, the issue of energy transformation. Okay. Mechanical to electrical, electrical to mechanical, right? And then the rules for motors is the left-hand rule. Okay. While remember, we drive motor vehicles on the left, so the left-hand rule, Fleming's left-hand rule, is the one that's either used to determine the direction of rotation or current in the coil or the magnetic field, right? And then there's one for alternating current, the one with the formulas that have to do with the subscripts. But having said that, remember, the easiest way to remember those things is to actually tabulate them. No, in a motor, this is what happens. These are the components. Where do you find a split ring? Where do you find a slip ring? Because those questions are basically type of, recall or remembering. So these are the easy marks. Here is a practical example of a question that deals with motors and generators. Okay, the focus in this case is on the main differences between a DC and an AC generator, right? Okay, if you look at diagram A, it's a machine. This machine is being rotated. Okay, so the input in this case is mechanical energy. Okay, the movement there of that coil in that magnetic field is the mechanical energy, which is the input. And then the output is electrical energy. How do we see the output of electrical energy in this case? Is the light bulb that will glow, right? So obviously A is a generator. Okay. What makes us say it's a generator is because we can see that while we input the mechanical energy, the output is electrical energy, right? And then the next step is to determine whether it's an AC or a DC. Now, that is nothing to do with energy transformation, because whether it's an AC generator or a DC generator, what actually happens is that mechanical energy is converted to electrical energy in both cases. So that doesn't distinguish or separate the two. The only thing that will separate those two is the components or the parts in that simplified machine. It's always a simplified diagram. Okay, that's why I'm emphasizing that. So if you look at this component here, that's a double C like that. Okay, that double C is double C. It's a split ring, double C, DC. Right? So once you see this part, which is exactly this, that's a double C there. So this is a DC generator. So if it doesn't have a double C or a split ring, it means it's an AC. Okay. Similarly, this one, we have to identify it whether it's a motor or it's a generator. Okay. We can't see much of input there in terms of mechanical energy, but there is a source there, right? This is a source of electrical energy, which we anticipate that it will cause a movement because there is that magnetic field from north to south there. Okay, it's always from north to south, right? Okay, and then because of this type of source, then this is a DC what motor. Also, why is it a DC? There is our double C there again. We're consistent with that. So once we see a double C, it's a DC something. As to whether it's a motor or a generator, it will entirely depend on the energy conversion. Right. So those are some of the easy marks that one may actually obtain. And then the other part in closing has a lot to do with the alternating current. Now, if you go back to the data sheet, if I can quickly go to that data sheet, if you look at this data sheet, these are exactly the formulae that you see under electric circuits. But what's so special about these ones is that they've got these subscripts, these writings that you see, RMS, average, maximum, when you copy these formulae, you copy them as they are, all right? Do not try to be fancy around it. For copying the formula as it is, including the subscript, you actually get the mark for the formula, provided you go on to make an effort to substitute. Okay, so if you copy the formula, you earn marks. Hence, we're saying these are our low-hanging fruits or these are our easy marks, right? So you must always refer to the data sheet, okay? Include the subscripts. Take note of the SI units, because the last mark for the answer is purely based on the what you call the correct SI unit, if it's a calculation, right? Be it a simple straightforward calculation, which is formula substitution answer, or it's a multi-step type of a problem or calculation, you also need to include the correct SI unit, right? Very, very important. Okay, and also we are able to apply Ohm's law, because remember, most of the questions on alternating current, they relate to like real life application, because in our homes, schools, everywhere, we make use of alternating current instead of the direct current, okay, except for the fact that we're experiencing a lot of challenges now in as far as the load shedding, but it's practically the what you call the alternating current, right? Okay, now because of time constraints, I would have gone on to look at, let's say, maybe photoelectric effect, work energy and power, you name it, but I think we tried to cover a bigger scope in terms of the technique without so much focus on the answers and the actual problems, just to give a sense of what actually one can do in terms of the technique when you respond to questions tomorrow. So if you answer all the questions that you have attempted within that 3 hours, it's also very important to go back, read the question, look at your calculation, look at your definition, ask yourself, have I answered the question? So in the 3 hours, there's no time for sleeping. which is very unfortunate. So look at the question. Once you are done, look at the answers. Ask yourself, have I answered the question? And try to answer all the questions, because in paper one physics, we are not given a choice to say we can choose. All the questions must be answered because of the 150 marks. Now, with that said, grade 12 learners, I just want to wish you everything of the best for tomorrow, and I most certainly hope this session was of enormous benefit for you, and in terms of maybe trying to prepare you adequately. I just want to wish you everything of the best from myself, Themba Ncube. Everything of the best for tomorrow, and bye bye.